Hello, this is a very special lecture. We have an ordinary differential equation of order 1, which we visited repeatedly. We approached it analytically, separation, similar methods. We approached it numerically, talking about Runge-Kutta methods and other methods. But now we will try something totally unexpected. Here we go. I see some expression featuring x, y, and y prime, so I can isolate y in any way I feel like. On the right, after I isolate y, there will be perhaps some x's, perhaps even some y's. Perhaps I didn't move all of them to the left. Okay, this can happen, and I definitely expect the derivative. Now I look at the right-hand side. It's some expression. And this expression features variable x, which is also hiding in y and in the y derivative. So in fact, the right-hand side is a function. So I can see it as a mapping. It's some sort of a mapping which takes my function y and does something to it. And this something includes taking a derivative. So this derivative now becomes part of the procedure which is hiding in t. So t is a mapping which takes functions and produces functions. And I'm looking for a function y, which if I put it into t, it stays the same. So in fact, the differential equation got transformed into a fixed point problem. That was unexpected. Let's have a look at it. Y prime is equal to y minus x. A very nice linear differential equation. So let's try our trick on it. I'm going to isolate y, and quite frankly, there is a natural way. So unless you want to do something really crazy, this is the way to go. On the right, we can see this mapping, ty. How does it work? It takes the function, differentiates, and adds another function, which is just x. Okay? Let's try it out. What happens if I substitute x cubed into this right-hand side taken as a mapping, as an operator? Well, I'm supposed to take x cubed to this function and differentiate it and add function x to it. And I get 3x squared plus x. That's it. That's the output of my mapping. So it takes functions and produces functions. Okay? Solving the differential equation is equivalent to finding fixed point of this special mapping. We should be careful because mappings always go from a set to the same set when you're looking for fixed points. So we should be careful. Probably we will again want to take set of functions which have all derivatives available. And then this mapping is defined well, things like that. These are technical problems. When we talk about fixed point problems, we also talk about iteration and about Banach fixed point theorem. So perhaps we should start talking about introducing some notion of distance into this space of functions, things like that. This can be done. It takes a while, so let's skip it and let's just play it by the ear. Okay, I see a fixed point problem, so I try iteration. Okay, iteration, how does it go? Well, we have to start somewhere. Let's say x cubed, good candidate. We already know how to work with it. When I apply the mapping t, I know what's going to happen. I just did it. 3x squared plus x. Okay, this is something like y0. This is something like y1. How about y2? So I'm applying the mapping t to y1 to get y2. So what's the prescription? I have to differentiate, and I get 6x plus 1. And then I have to add x. Okay, do I want to simplify? Not really. But I will simplify in my head in a second. So to get y3, I have to take derivative of this, and now I imagine that it's 7x. So I take derivative, I get 7. Derivative of 1 is 0, it's gone, and then I add x according to the formula. Okay, let's apply t again. I take derivative, and I add x. Let's apply t again. I take derivative, and I add x. Wow, let's apply t again, and again, and again. So it seems that y-ends converge to the function yx, which is 1 plus x. So what did we just do? this fixed point iteration actually converges in a very surprising way that we actually obtain the limit at a specific time after finitely many steps, and then we just stabilize. And this function is a fixed point of this mapping T, and it indeed solves this differential equation. We can check. We take this function 1 plus x, we substitute it here. 1 plus x minus x, that's 1. And when we differentiate, we get 1 again. Yeah? Left-hand side, right-hand side, they agree. Wonderful. So, this is actually a very nice example that the transformation of a differential equation into a fixed point problem can work. Now, the disadvantage is that it's sort of, it's not exactly the most flexible way to do it, and that's why people actually don't use it, essentially. Now, let's have a look at some experiments. So here I have my function x cubed, and I apply the transformation to it. So I differentiate and I add x, and I get 3x squared plus 2. This fits. And now I just recycle this line in my code, and I will see formulas which we can see over here, and eventually they should stabilize to 1 plus x, and they did. Wonderful. What happens if I start with, let's say, x squared? That's a good question. Well, again, I'm recycling this formula, and I got stabilization. That's very nice. What happens if I try exponential function, e to x? Okay, I start taking derivatives, and I got another stabilized situation, and this is actually another solution of our differential equation. Not the same, but a different one. So this is not too bad. Okay, what happens if I try the sine function as the starting point? I start applying my mapping, and I can see that this kernel 1 plus x is always there, but then this part is changing, and actually there's a period of 4. After 4 iterations, I'm back to where I started. So I'm getting divergent sequence of functions which is divergent. So yeah, this didn't work out. Sine didn't work out. So much for this example. It was a little bit optimistic because it showed that the fixed point approach could work. But as I said, this is not the best way to do it. For the best way, we have to revisit our general setting and recall motivation for Runge-Kutta methods, which was through integration. I changed differential equation, actually initial value problem, into an integral problem. And that's exactly what I'm going to do here, but there is a difference. When I was motivating the Runge-Kutta methods, I was integrating over a fixed panel. But now I want to integrate over range where the right endpoint is movable, so that the outcome is a function again. Now this is actually the setting of the fundamental theorem of calculus. So this is quite familiar. Let's have a look at it. I have my differential equation, but I'm going to change the variable so that x is free now. Y prime t is equal to ft yt. And initial condition, y at x naught is y naught. Here we go. I integrate from x naught to some unknown x. When I integrate on the right, it will be simply integral from x naught to x, ft yt dt. Now you can see that it makes sense. X is used here as a variable upper limit, and then I have to use a different letter for the working variable here in the integral. When I integrate on the left, it will be y at x, according to the fundamental theorem of calculus, and y at x naught is subtracted. And y at x naught is y naught. I move it to the right, and I get this. Yx on the left, that's some function. On the right, there will be y naught plus integral x naught to x ft yt dt. And on the right, that's another function as a whole, as a unit. This is a function with the variable x. So there are two functions with the variable x, and this one is actually based on y again. I can take this right-hand side and consider it a mapping or an operator which acts on y. Let's call it ky. This is actually a traditional notation for this type of trick in some applications. So this is a good name, ky. So I'm looking for a function y, which, if I do this to it, I will get y again, a fixed point problem. Let's return to our example. Y prime is equal to y minus x. Okay, I like myself, so I start my initial condition at 0, and I'll make it 1. Now I imagine that the variable here is t, and I integrate. So I get integral from 0 to x, yt minus t dt. And when I integrate on the left, I have to substitute here. Okay, I will do it in general. There will be some initial value here, y naught, and I move it to the right. And on the left, there will be yx. So that's the transformation of this particular differential equation into integral form. And what we see over here, that's the mapping ky. It takes function y and changes it according to this formula. Okay? And I will first try it with initial condition 1. Okay, let's write it down. Ky for me now is 1 plus integral from 0 to x yt minus t dt. That's the formula that I will focus from now on. Again, let's experiment. How does this mapping influence the function x cubed? Okay, I'm not really happy about integrating x cubed, but it's fair to check it because we tried x cubed here. Yeah, let's try it also here. So what does the mapping k or the operator k do to this function? Well, it starts with 1, and now we should integrate from 0 to x this function, but with the variable t cubed minus t dt. How much is it? Well, 1 plus, now we take antiderivative, 1 over 4 t to the power 4 minus 1/2 t squared from 0 to x. And finally, we evaluate. Actually, I'm going to switch the order of powers because I like it better when they go one after another. So it will be 1 minus 1/2 x squared plus 1 over 4 x to the power 4, and that's it, because when I substitute 0, I get zeros. So when x cubed is used as input for this mapping k, this will be the output. Interesting. Now we understand the meaning of the right-hand side, how it works, the mechanics. And again, we can ask, how do we get a fixed point for this type of problem? Well, let's try iteration. Here we go. Where do I start? Okay, I don't feel like starting with x cubed. Let me start with x. For integration, I prefer it. So, when I apply k, I get y1, which is, let's see, here is the formula. 1 plus integral from 0 to x of my function, which is t minus t dt. Well, that's actually fairly simple. T minus t cancels. Integral of 0 is 0, it's just 1. So far, so good. I apply k to this function, and I get y2. y2 is 1 plus integral from 0 to x, integral of this function minus t dt, which is, okay, 1 plus antiderivative is t minus t squared over 2 from 0 to x, and I'm getting 1 plus x minus x squared over 2. Okay. I apply mapping k. y3. How many times do I want to do? The answer is until I can see the pattern. So let's be patient. Should I ask Maple for it? We are tough. We can fight it out. Okay. How do I get k of this? I have to start with 1. I have to integrate from 0 to x. Now we're integrating this function, 1 plus t minus t squared over 2, and I'm subtracting t dt. So this will be 1 plus antiderivative to 1 is t. T cancels, and I'm taking antiderivative to this part, which is minus t cubed over 6 between 0 and x. And therefore, y3 is 1 plus x minus x 3 over 6. applying k again. Do I see something? Okay, I'm vaguely starting to see something, but let's be sure. So here I put some continuation mark. Okay, which mark did I choose? This one. Why not? Okay, continuation mark. I'm applying to y3 my mapping, and I'm getting y4. 1 plus integral 0 to x. I'm integrating this baby, subtracting t dt, which is 1 plus integral t, this t cancels, minus t to power 4 divided by 24. And I'm getting mightily suspicious, so I'm going to write it in a slightly different way. This is actually x to power 4 divided by 4 factorial. And it fits. X squared divided by 2 factorial, x cubed divided by 3 factorial. Here it doesn't work, but I can write it like that. 1 plus x minus x to power 1 divided by 1 factorial. It all seems to fit. So my suspicion is that yn is 1 plus x minus 4 indices fit x to n over n factorial. This is my suspicion. And I can prove it using mathematical induction. Now, key question, what happens when we send n to infinity? I have a sequence of functions. So I'm asking for convergence of functions, and this is always done on some interval, on finite intervals. And over here I have a power divided by factorial, and it's a known fact that as a function this disappears on finite bounded intervals. So this disappears, this goes to 0, and the limit is function 1 plus x, which is exactly the solution to this differential equation, but also to the initial condition. If I put 0 into it, I get 1. So this is really the solution to our initial value problem. Wonderful. Let's go to Maple and check that it actually works. So I start with x, and now I start substituting, and we are so far seeing stuff that we saw before. Now we are at y4, and let's see y5. Will it follow the pattern? And the answer is yes. So the pattern is over here. You can see it clearly. Wonderful. And therefore, it seems that this actually works. Let me try a little trick. Instead of 1, I'm going to put there some constant. Let's erase. Let's have a look at it. I will again start with y0, the function x. This time I will be using this iterative formula with y0 instead of 1, and I am not going to do it by hand, definitely not. So let's go here. Y is equal to x, and I will skip to the last line in this code where I'm actually using y0, and then I'm integrating and so on. Here we go. This is y1. This is y2. This is y3. This is y4, y5, y6. Okay, what do we see here? We can see that the powers actually multiply in numbers. Once a power appears, it never goes away. So there are more and more powers as we go. This is y6. Most of those powers, they have the same pattern, but some of them, well, one of them is different. This one does not feature y0 in the formula. Okay? So this one is special. Let's try to guess what the general pattern is. yn. How much is yn? Well, let's see. Okay, I shouldn't forget, there is extra guy at the start, y0. I will like it to have it here. Then there is y0x. Then there is actually y0 minus 1 times x squared over 2. Then there is, okay, y0 minus 1 times x cubed over 3 factorial. We can see 3 factorial, so this is 2 factorial also. And we keep going. And this pattern continues until we hit a specific power, and the next power is different, and it's the same power as is the index, if I counted it right, index of the iteration. So at the end, it's subtracted, and it's x to the power n divided by n factorial. So the last guy has x to n minus 1 over n minus 1 factorial, and there is this y naught minus 1. This should be it. Let me try to run it again, and we will check that this actually works. So x naught, x1, for 1, this is special, x2, and now we are beginning to see it. x2 should have x squared divided by 2 factorial as this separate term, and it does. So far, so good. x3, x4, yeah, this fits. x4 has x to the power 4 divided by 4 factorial as the special power, and the powers with pattern, they stop with 1 power less. So this seems to fit. Okay, let's have a look at it. Okay, I would like to treat this as a unit, preferably using some series notation or summation notation. And for that, I would really appreciate if also here I had y naught minus 1. That would be really, really neat. So what I'm going to do, I'm going to introduce it there artificially. I subtract 1, and I have to add 1 to balance it off. I subtract x, and I add x to balance it out. Okay, here, y naught, I subtracted 1, and I subtracted x. Let's check that it's the same. Y naught minus 1 plus 1 cancels. X minus x cancels, y naught x, it works. And the rest is the same. Okay, let me do it like that. And now finally, I can write a very nice formula for the nth iteration. It's 1 plus x, then there is y naught minus 1 times summation k going from 0 to n minus 1, x to k over k factorial. This takes care of this first part, and then there is this extra power, minus x to power n over n factorial. So that's a nice formula, and I ask what happens when n goes to infinity. And the answer is that I get a limit. How do I know? Well, first of all, 1 plus x, that's a constant. It's a function, but in the as a sequence of functions, it's a constant sequence of the same function. Then there is y naught minus 1, and we know what's happening here when we send n to infinity. We get Taylor series, which is actually quite known. If I put infinity here, this becomes exponential. So it's e to x. That's very nice. And finally, there's this power, and again, we are doing limit on a finite interval, a bounded interval like that, and this goes to 0. So in this case, the fixed point iteration also converged, although it took more work. We had to integrate, well, Maple did it for us, and it converged to a specific function. Now we can read this in several ways. Y naught is some constant. Y naught minus 1 is also a constant. We can give it a name. 1 plus x plus c e to x. This is actually a general solution for this differential equation. You can easily check. Or, okay, it's a linear differential equation. You can apply the tricks that we know for linear equations, and you end up with exactly the same thing. So we obtained a general solution. Or if you are solving initial value problem, you simply take the value y naught, you substitute it here, and you get a particular solution. That was wonderful. And we got all this from the fixed point iteration. Now, this approach is much more fruitful also for theory, because the action of this operator, of this k, can be analyzed. And in many situations, we can actually introduce the notion of a distance for functions. And we can ask a good question. Okay, I have two functions. They have some distance. Now I put them into this type of operator. And I look at the output. Are they closer or not? And it all depends on this right-hand side of the differential equation. And if this right-hand side is reasonable, then yes, we do get a contraction. And we can actually apply the Banach fixed point theorem. So the Banach fixed point theorem is really general. It can also help us with spaces of functions, with solving differential equations. And it is actually used also in theory. If you remember, we had a theorem on existence, Picard theorem on existence and uniqueness. And the fact that the given differential equation has a solution is actually proved traditionally using exactly this type of iteration. Just it's much more difficult because you don't have a specific formula. You have the right-hand side here, just like we see it over here. So the calculations are theoretical, they are more demanding, but the general idea is actually just like that. So that was an interesting visit which connected the questions of differential equations, or the problem of differential equation, and the interesting idea of fixed point iteration in a very general setting. I think it was worth the visit, although, of course, this was a bonus. We are not expected to see this on a test. And I hope you enjoyed it. And now this whole chapter is closed, and the next lecture will start something totally new. See you.